So for the longest time, our mental image of planet formation, it's been these big protoplanetary disks, right? These swirling clouds around young
Yeah.
stars.
Yeah, exactly. Gas and dust.
And the story was always that they just shrink. They thin out, like material feeds the star, clumps form planets, and the disk gets smaller.
That's been the standard picture, yeah. Like a cosmic ice sculpture just sort of sublimating away.
But there's this recent study, it's thrown a bit of a curveball, hasn't it? Suggesting maybe the sculptor adds more clay.
That's a great way to put it. Yeah, we're doing a deep dive today into some new research that really challenges that traditional view.
Okay.
Our source material, it shows something quite surprising.
Yeah.
Young stars, well, in the right places, can actually pull in more material.
More material, so extending the life of the disk, maybe making it bigger.
Exactly. Extending its lifespan, increasing its size potentially. It changes things.
Okay, let's get into this then. So it's not just this slow dwindling process. These stellar nurseries can actually get topped up. That's unexpected.
It is. And the core idea we're exploring is how young stars, interact with what's around them, their environment, and how that shapes planet formation.
Right, and there's a specific process involved.
Yes, we're focusing on something called Bondi-Hoyle accretion. This study suggests it's actually much more important for how these protoplanetary disks evolve than we've previously thought. Those beautiful swirling disks,
Bondi-Hoyle accretion.
Right.
Okay. And the source for all this, where's this coming from?
We're looking at a really interesting study published in Nature Astronomy. It was led by Paulo Padoan. He's originally from the University of Barcelona, now at Dartmouth College.
Gotcha. So our mission today, explore this new discovery, see how it kind of redraws the map of planet formation, and, well, the exciting bit, what it might mean for finding habitable planets.
Exactly. It feels like we're adding a really significant new chapter to the story of how solar systems like ours, or maybe very different ones, actually come together.
All right, so let's start with the contrast, the old view versus this new one. Lay out the traditional model for us again.
Okay. So for ages, the model is pretty straightforward. A disk forms around a brand new star. Then its life story is mostly about losing mass.
How so?
Well, two main ways. Material spirals onto the star itself, gets eaten, basically, and then particles in the disk collide, stick together. You get planetesimals, the building blocks, and eventually planets. So the disk material gets used up.
Right, so it's either flowing inwards or getting locked up into bigger things within the disk. A closed system, more or less.
Pretty much.
Yeah.
But the key change this new research brings is realizing these young stars aren't, isolated islands.
Oh, okay.
They're born inside these huge molecular clouds,
Yeah.
often in clusters with lots of other stars nearby. And that environment isn't just scenery.
It's active.
Very active. The study shows these young stars can actually pull in extra stuff, gas and dust, from that surrounding birth cloud.
Whoa. Okay, so this is where it gets really interesting. It's not just the disk material moving around. The star itself is like a cosmic vacuum cleaner, pulling in fresh supplies.
That's a good analogy. Yeah, it's pulling in fresh ingredients from its neighborhood. And the mechanism is this Bondi-Hoyle accretion.
Explain that a bit more. Bondi-Hoyle, how does it work?
So basically it's about gravity. As the star moves through the gas and dust of its birth cloud, its gravity captures some of that material.
Okay.
Think of like a massive object moving through, say, thick fog. It pulls some of that fog along with it gravitationally. Here, the fog is the interstellar gas and dust.
And what affects how much it pulls in?
Several things. The star's mass, heavier stars pull more. Its speed relative to the gas, slower stars moving through dense gas capture more effectively. And of course, how dense the gas cloud actually is.
Right, denser regions, slower speeds, more pull. Makes sense. But the study mentions this doesn't hugely change the star's own mass. How can it still be a big deal for the disk?
Yeah, that's a really crucial point. The amount of mass captured through Bondi-Hoyle might be small compared to the star's total mass. But for the disk, it can be significant.
How so?
Even a relatively small inflow of new material can make a difference. It can replace material that's falling onto the star or forming planets. It can essentially keep the disk going for longer or even help it grow larger.
Okay, yeah, I can see that. Like adding water to a leaky bucket, it takes longer to empty. Maybe never does if you add enough. Now, you mentioned the birth environment, the star clusters. How important is that context?
Oh, it's absolutely fundamental. Like we said, stars usually form in these crowded clusters inside giant clouds. They can spend millions of years embedded in this gas-rich nursery.
And that provides the fuel.
That's the reservoir. It's the source of the raw material needed for Bondi-Hoyle accretion to actually happen effectively. If a star formed way out on its own, Far from any gas reserves, this process just wouldn't have much to work with.
So being born in a crowd can actually be good for the planet-forming potential, in a way. That's interesting. It sort of pushes back against the idea of just isolated stars evolving.
It does. But there's another layer of complexity. The gas itself isn't smooth or still. The study talks about turbulence, the chaotic motion of this interstellar gas. What's that about?
Ah, turbulence. Right, so the gas isn't just sitting there waiting to be grabbed.
Not at all. The interstellar medium is incredibly dynamic. It's swirling, churning, gas moving in complex, somewhat unpredictable ways. And this turbulence really matters for Bondi-Hoyle accretion.
How does it affect it?
It can be tricky. Think about trying to catch something in a strong, gusty wind versus a gentle breeze. The chaotic motions can sometimes help bring material closer to the star, enhancing capture, but other times it might disrupt the flow, hindering it. It really depends on the local turbulent conditions.
So understanding the local cosmic weather, the turbulence, is key to figuring out how much material a star can actually gather. And the study needed to model this. That sounds hard.
Incredibly hard. Modeling turbulence is a major challenge in astrophysics. You've got huge scales, from entire clouds down to a single star's gravity. The physics is complex.
So how do they do it?
This is where you absolutely need powerful computer simulations. You can't easily solve the equations on paper for these kinds of chaotic systems. Simulations let researchers track these complex interactions over time.
Okay. And bringing this back to the disk, what's the ultimate effect of this accretion, this replenishment? How does it change the picture for planet formation?
Well, the really significant thing is that Bondi-Hoyle doesn't just bring in mass, it also brings in angular momentum.
Angular momentum spin, basically.
Exactly. More spin allows the disk to be larger, more spread out. And having larger disks with more angular momentum actually fits much better with what we observe.
Observe how?
With telescopes like ALMA, the Atacama Large Millimeter Submillimeter Array, ALMA gives us amazing images of these disks, and many of them look quite large.
Yeah, so the older models maybe struggled to explain how disks got so big?
Sometimes, yes. If you only considered the internal disk physics, it was sometimes hard to account for the sheer size of some observed systems. This external accretion helps resolve that discrepancy. It provides both the stuff and the spin needed for bigger, longer-lasting disks.
So it's like the environment is giving the disk a vital boost. More time, more material, potentially leading to maybe bigger or different kinds of planetary systems?
Precisely. It really means we need to revise our models quite significantly. Models of how disks evolve and how planets form within them. We can't just think of them as these closed, winding down systems anymore.
The outside world matters.
The outside world plays an active, ongoing role.
Yeah. Okay, this sounds like a big shift. What's the evidence underpinning it? How did Padoan and the team actually show this was happening?
They used a really powerful combination of methods. State-of-the-art computer simulations were key.
The ones modeling the turbulence and star formation.
Exactly. They simulated stars forming inside these turbulent gas clouds, and they could track in detail how the stars pulled in material via the Bondi-Hoyle process. But crucially, they didn't stop there.
They checked it against reality.
Yes. They compared the results from their simulations, things like disk sizes, accretion rates, with actual observational data from ALMA, seeing if the virtual nurseries matched the real ones.
That sounds like a huge amount of work, computationally and observationally.
It really is. And one of the researchers involved, Veli-Matti Pelkonen, made a great point about this. He emphasized how simulations let us see things we can't directly observe.
Like what?
Like the underlying structure, the density, the velocity of the gas, how magnetic fields are behaving deep inside these clouds, and how it all changes over millions of years. The simulation showed Bondi-Hoyle accretion was really kicking in, especially later in the star formation process, feeding the disks.
And Pelkonen also mentioned future tools, better computers, the James Webb Space Telescope.
Right. As computers get even faster, the simulations can become even more realistic, include more physics. And telescopes like JWST, seeing in infrared, plus continued amazing data from ALMA in millimeter waves. They give us unprecedented views of young stars and disks.
So theory and observation are working together more closely than ever.
Exactly. It's that synergy. We can test the simulation predictions against increasingly detailed observations and refine the models. It's a really exciting time for the field.
This paints a much more, interconnected picture. Planet birth isn't just happening in the disk, it's strongly influenced by the wider cosmic neighborhood. What does this mean for the big question, the search for life elsewhere?
Well, if you think about it, the conditions in a protoplanetary disk are fundamental for forming habitable planets. You need the right materials, enough time, the right location, the habitable zone for rocky planets like Earth to form.
Okay.
So if Bondi-Hoyle accretion helps create larger disks or makes them last longer, or maybe even affects their chemical makeup by bringing in fresh material,
then the environment where a star is born could directly influence whether it's likely to form planets that could support life.
that's the implication, yes. Those potentially crowded, turbulent stellar nurseries might actually be more conducive, in some ways, to producing the kinds of planetary systems we think might be habitable. It links the large-scale structure of star formation to the small-scale details of planet formation.
So the fact that star clusters are common, that gas clouds are turbulent, these aren't just background details. They could be key factors in how many potentially living worlds are out there.
It certainly suggests that, yes. The birth environment seems to be an active player in writing the story of planet formation, not just the stage it happens on. It could shape the conditions needed for life to emerge.
Wow. Okay, let's try and boil this down. What are the absolute key takeaways from this deep dive?
Okay. First, the old idea of disks only shrinking. That needs a major update. They can grow, too, by pulling material from outside.
Right. Replenishment is possible.
Second, the star's birthplace, especially being inside a dense, gassy cluster, is really important. It provides the fuel.
The environment matters.
Third, the mechanism for this refueling is Bondi-Hoyle accretion. Gravity pulling in surrounding gas and dust.
Got it. Bondi-Hoyle.
And finally, this changes our models of planet formation quite a bit. And tantalizingly, it might shift our perspective on where the best places are to look for habitable planets beyond Earth.
It's genuinely amazing, isn't it, that something as fundamental as how planets form is still seeing these big revisions? Really shows how much we're still learning about the universe.
It absolutely does. It keeps things exciting. And it leaves you, the listener, with a pretty big thought, doesn't it?
Which is?
Well, now that we understand the birth environment plays this active role, how does the sheer number of stars born in clusters across the galaxy affect the odds? The overall potential for habitable planets out there?
That is a powerful question to chew on. How common are the right conditions boosted by this accretion process? Makes you wonder what other cosmic assumptions might get overturned next. Thanks for unpacking all this today.
My pleasure. Fascinating stuff.